Good morning, everyone. I am Aditi Raste. I will be presenting SLIM, a high-level abstraction on LLVM IR suitable for program analysis. On behalf of my team, that includes Aditya Pradhan, Akshat Oak, and Uday Khedker. So this is what I'm going to cover today. I'll start with the introduction, followed by the features and applications of SLIM, and conclusion and the future work. So what exactly is program analysis? Program analysis is the process of discovering information about a program. This information is then used in compiler optimizations, bug detection, verification and validation of programs, software maintenance and enhancements, and basically understanding of the source program. LLVM is a very well-known compiler framework which is used in the industry as well as in the academia. And the reason for LLVM's popularity is its well-designed intermediate representation, LLVM IR, with the help of which it is easy to add passes into LLVM. However, program analysts often find it challenging to interpret the LLVM IR, primarily due to the plethora of details that are embedded into the LLVM instructions. At times, these details are extraneous for majority of analyses. So let's take an example for this. There is a source program here and the corresponding LLVM IR. Now, this source program is a very basic source program, just consists of pointers. But when we add aggregate data structures, arrays, structures to structures, nested structures, it definitely will complicate the LLVM IR. Right now, the details that are highlighted in red, they are unnecessary for most of the analyses. Also, there are a couple of observations here. LLVM may generate multiple IR instructions for a simple statement in the source program. So as you can see, for a return statement in the source program, LLVM IR has generated 3 instructions. Also, LLVM instructions are based on load and store architecture, because of which the operands are always accessed via a pointer and never directly. Now, this adds an extra level of indirection to the source programs, and this conflicts with their original definition. Like, for example, in the source program, we see that x and y are the variables. They're defined as pointers, but in the LLVM IR, they are used as pointers to pointers. Also, apart from the original operands, an LLVM IR instruction may also contain some compiler-generated temporaries, debugging information, alignment specification, etc. So there is a need, particularly for machine-independent analyses, for an abstraction layer over the LLVM IR that will extract only the relevant information from the IR while ignoring the rest. This is where I introduce SLIM, which is a simplified LLVM IR modeling. SLIM is a conceptual framework that provides an abstraction over LLVM IR. SLIM models the LLVM IR instructions in a clean and simplified manner by hiding the low-level details. SLIM also reduces the number of instructions that an analysis needs to consider. Let's go back to the source program. This is the SLIM that is generated for the source program. Let's see what information is provided by SLIM. So SLIM gives us the source file name. It gives us the function name, the basic block details, and the instructions. Please note that these instructions are pretty similar to the source program statements. Every instruction is associated with a unique instruction ID, and SLIM also provides us with the source line numbers. Please note that the instruction ID and source line numbers need not match. The reason is instruction ID is unique across all the files, and source line numbers, of course, are specific to a particular source file. Okay, now let us see LLVM IR and SLIM together. So this is our source program. For this source program, we have just seen the LLVM IR in the previous slides and the SLIM, corresponding SLIM generated for the source IR. Now, if we look at the instruction, the statement number 7 in the source program, star z equal to y, we can see for this source program statement, LLVM IR is generating a sequence of instructions, and SLIM has only a single statement, star z equal to y. So we can see that SLIM eliminates temporary variables as far as possible, and SLIM also combines multiple instructions into a single instruction. Now let me proceed to the features of SLIM. So SLIM generates a modeling that is clean, simple, closer to the source program, and yet it is in 3 address code. SLIM eliminates the extra level of indirection of the source variables. It explicates the source variables that are used in the instruction, and SLIM provides an abstraction to eliminate temporaries and obtain the source variables. Also, SLIM performs formal to actual argument mapping for a call by adding assignment statements before the call instruction. So by using source variables instead of temporaries, in our experience, we have seen that instead of using the source variables instead of temporaries, it increases the scalability of context-sensitive inter-procedural analysis significantly. Also, SLIM extracts the relevant information from LLVM IR. So by relevant information, I mean the operand names, the operand attributes such as whether the operand is global, aloca, GEP operator, also field indices if they are associated with the operand, the type of the instruction, and the data type of the operand. Irrelevant information such as alignment details, keywords, comments, and size of the data types are ignored by SLIM. Now, these are some of the applications where we are using SLIM. Most of this work is published work, and a couple of projects are also in the process of getting published. So we are using SLIM for context-sensitive top-down pointer analysis, GPG-based bottom-up points to analysis, construction of context-sensitive SSA, liveness-based flow and context-sensitive points to analysis, we call it LFCPA, and LFCPA with bypassing by LFCPA. And we use SLIM as the underlying IR in VASCO. VASCO is a framework for interprocedural analysis using value-sensitive contexts. So SLIM provides a clean abstraction over the existing LLVM IR by hiding low-level details, facilitating efficient program analysis. SLIM enables easy analysis by modeling only the relevant details of the LLVM IR. We agree that the relevant details will be different for different analysis, and therefore SLIM can be easily adapted to encapsulate the fundamental aspects varying with different analyses. Also, we intend to make the SLIM repository publicly available after this presentation. As future work, currently the instructions in SLIM can only be read but not modified. So we want to support transformations in SLIM, such as to add an instruction, delete an instruction, replace a variable or an expression, etc. Also, there would be a need for generating LLVM IR from this transformed SLIM. Also, addition and the future work also includes to add an abstraction for diffuse edges and enhancing SLIM with context-sensitive interprocedural LFCPA. We have seen discussion on this in the morning session. I'm referring to the talk by Preetham and Supriya. Currently, SLIM is using the control flow provided by LLVM. So we want to extend SLIM in order to support control flow for efficient analysis. Acknowledgements. SLIM represents the culmination of collaborative efforts by multiple individuals engaged in program analysis at the Indian Institute of Technology, Bombay. We are grateful to Rishabh Sharma, who is the developer of Spatial, a framework to easily implement any analysis on LLVM IR. Spatial provided the initial spark for the development of SLIM. We are thankful to Swati Jaiswal for her valuable contribution in the design of SLIM. We extend our appreciation to Supriya Bhide, Manjushri MP, Shri Devi Harish, Ruchika Shirsat, Nilesh Shirsagar, Shreya Singh for their valuable contribution, insightful feedback and discussions. Actually, Supriya, Shri Devi, Ruchika and Akshat, they are all here for the presentation. That's all from my side. Thank you very much.
So I was wondering, so SLIM is applied on top of LLVM IR and it's sort of a layer of abstraction, right? And then you mentioned LFCPA by LFCPA are two analysis that can be done on top of it. So these analyses, they are done automatically or is it done manually first? And if it is done automatically, so in some sense, this automatic flow of creating this abstraction on top and then doing these LFCPA helps in maybe a more optimized output of the code. Am I understanding this correctly?
First of all, what exactly you mean by done automatically?
So this analysis, LFCPA that you're doing on top of the SLIM,
yes.
yeah,
yes.
Is that automated?
No, it's not automated.
Okay.
We will be performing on. We are providing an abstraction on LLVM, which is SLIM, and on this abstraction, we are running the analysis, any analysis. LFCP is just one example of. So, there's a definition of automatic clearing. There's a code that runs and performs. Right. Is that automatic?
Well, yeah, that's
okay. No one manually looks at the code.
Yeah, that's yeah. So I was wondering, so you came with these are the important details, these are not the important details. So the reason why I asked this question was, how did you decide that these are the details we need and these are details that you may not need? Yeah.
Yeah. So we started the different program analyses, and in general the program analyses require the relevant details that have been specified in the table. So this SLIM abstraction is specifically for to ease the life of a program analyzer. So, and also I've always mentioned that in case if there is another analysis which might require alignment details, then SLIM can be readily adapted to include them. So as of now, SLIM is providing or considering these this information as relevant, but it can be extended to include the other information as well.
I had a question.
Yes,
do you generate SLIM from source or is it reverse engineered from LLVM?
We generate it from LLVM. It's an abstraction over LLVM IR. So we generate it from LLVM, yeah.
Is it inferred from LLVM?
Yes, LLVM IR.
Okay, not from the source side.
No.
Because you mentioned that you want to regenerate LLVM IR.
After we perform, currently we are not performing any transformations on SLIM. So after we transform SLIM, we want to get back, we want to generate LLVM IR from the transform SLIM. Yes, sir.
Hello. Yeah, Bernard here from Qualcomm. So interesting talk, and I think you are doing an abstraction after LLVM IR, right? So what about the information from the source? So basically, when we are doing analysis at LLVM, sometimes we are losing the source information. And there are people working in this area, like from trials of bits, working VAS, which basically MLIR dialect, which bridge the gap between Clang AST and LLVM-IR, right? So what Slim is solving, why it is important, and is there a gap that bridge between the source information? Because since you are starting from LLVM-IR, it is because then we only have what information LLVM-IR have, right? And there is no way that I mean, of course you can get a debug information, but still limitation to what LLVM-IR. So if you are providing an analysis which LLVM cannot have, then can the analysis also reconsidering, I mean, also having information from the Clang AST?
Okay, so Slim is not created to replace LLVM IR. Slim is not a replacement. Slim is just an abstraction over LLVM IR. And the need for Slim is because we program analysts find it difficult to interpret the LLVM IR. So we are just trying to ease the life of program analysts by providing only the relevant information for a particular analysis.
Okay, thank you so much.
Thank you.
Hello, am I audible? Yeah. My question is in similar lines for with that gentleman that why didn't you try implementing this in MLIR? Because it's a straightforward dialect that you can see because you have source level information. You can put custom operations which resemble the ones you showed us on the slides, and it will be a very straightforward workflow.
Yes, sir, please.
We have spent 1 year, MLI doesn't work. MLI doesn't have a C interface. It takes from Python. Okay, we spent a year looking at that. Eventually we realized that MLI is not suitable for this because as she said, this is not a replacement for LLVM-IR. And we're using LLVM-IR because we want the SSA information that comes with menu res path. So on top of that, we're building an abstraction so that you can get exactly what you need, no more, no less. That's right.
Thank you.
Yes, we spent, after talking to Uday Reddy, I finally concluded. He's the one who said, forget this part, what you're doing is right.
Thank you.
Thank you.